So today we're going to be talking about logarithmic and exponential equations, pretty much what the duration of this chapter has been leading up towards. And so ultimately you're going to see a lot of overlapping ideas from previous sections. We also went ahead and added an additional logarithmic rule. So the first one, the third, fourth, and fifth, those should all be familiar from the previous section. The second one here is new now that we're introducing equations. And so what this says is if you have two logarithms equal to each other without any numbers in the front or anything like that, then the logs cancel out and you get whatever the logarithms are evaluated. We'll see this in a bit. So let's go ahead and just start looking at these examples. So this whole section is going to be me working out a bunch of examples. So there's nothing really new besides for this idea. And we'll start off with problem one, just to motivate what it means to solve a logarithmic equation. So solving means get x by itself. So generally what we would do is if the x is trapped within the logarithm, that idea that we mentioned in the previous section, using this idea of rewriting the logarithm as an exponential, which is also accommodated by this this loop method or whatever you want to call it. So that tells us how to order this thing as an exponential. It says 2 is the base raised to the third power is equal to what the arrow is pointing to, 7x. And from here, well, 2 to the third is 8. And then we simply divide by 7 to get that x is 8 over 7. So that's just kind of a warm-up idea to motivate this section. And we will be using this theme throughout. It may not be presented as nice of a form as this one. So let's look at problem 2 though. So problem 2, what's interesting is that it has 2 logarithms. Before we didn't have that, we just had 1. So when we have 2 logarithms, well, when you try to think about that loop method, it gets a little bit messy. So something I would recommend as we start to get 2 or possibly more logarithms in the equation, it might be good to scan all the logarithms and see if any of these can simplify to a nice number. Because I see log base 5 of 10 over here, so this is scratch work off to the side. Log base 5 of 10, well, that's the same thing as log of 10 divided by log of 5. And so it might be worth asking yourself, does that simplify to something nice? And if you put it in your calculator, you will end up finding out that it does not simplify very nicely. I get 1.43, it's an irrational number. The decimal goes on forever. So the fact that we can't simplify this means we cannot get it into this form. So instead, we want to utilize this second rule here. This is kind of the new idea. And we actually kind of used this idea when we looked at exponential equations. When you had 2 exponents equal to each other, or 2 exponentials equal to each other, and the bases were the same, then you were able to cancel out the bases. It's the same idea here. Notice we have 2 logs, there's no numbers in front, so there's no factors that we have to move as exponents. The simple idea here is that these logs cancel. So that's what the second rule over here says. It says if the logarithms are equal with no interference anywhere around the logarithms, then we can cancel out the logarithms. And so what that leaves us with is x plus 3 is equal to 10. That's it. See how nicely that's simplified? So if we can get to a form like this, it's very nice because it's something we can quickly jump to. And so from here, It's just a matter of subtracting 3. And we get that x is 7. So let's go ahead and look at that same idea over here. Now you can technically, on this problem, you could try to use this method. However, I think it's more convenient to scan the whole problem and see if there's anything worth simplifying. So notice right here, this is all numbers. There's no variables in this expression here. Let's see if we can simplify it into something nice. So this would be scratch work. In fact, I'll do it all the way over here. So that is log base 8 of 64, and I'll leave the negative sign there. So I'm leaving the negative off. So log base 8 of 64, which is what we have over here. If we wanted to try and put this in our calculator, it's exactly this. And if you put this in your calculator, you will end up actually getting 2. So it does work out really nicely. And we can go ahead and rewrite this problem as such. So that's 2 log base 8 of x. Remember, we didn't have the negative sign over there, so we'll put it, negative drops down. Log base 8 of 64 is 2. And so notice the problem simplifies very nicely because we observed a situation where we can simplify the logarithm. So now you might think, all right, so this is in this form and we can do the loop method, which would be okay, but this 2 is preventing that from happening. We cannot use the loop method until all numbers in the front are, well, moved. So this is when we would have to, so notice that corresponds with our initial form here. Notice this formula only works if the logarithm has, well, no numbers in front of it. It's just a bare logarithm, no numbers around it. It has to be isolated, fully isolated. So that's a matter of utilizing the power rule that we talked about previously. In fact, I rewrote it down here. We're just going this direction with it. We're taking numbers in front and bringing them as an exponent of the corresponding logarithm. And so now we have log base 8 of x to the second power is equal to negative 2. So notice the 2 became the power of x. That's the power rule here. And now that we got rid of the 2 in the front, we can go ahead and use that loop method. Which tells us exactly how to reformat this as an exponential. It says it's 8 raised to the negative second power is equal to x squared. And so now that we're here, well, 8 to the negative 2, hopefully you remember what a negative exponent does. The negative will flip the base, so then the negative would make 8 become 1 over 8, and the 2 would square that to give you 1 over 64. Or if you're not comfortable with that, you can type in 8, put the caret, now we use parentheses for negative 2, close parentheses, 0.015625. We'll convert that to a fraction to give you 1 over 64. In any case, this value is 1 over 64, and that's still equal to x squared. So now we just have to get x by itself. And the way we get x by itself, we square root both sides. So we'll go ahead and square root both sides to give us x is equal to, well, plus or minus the square root. Remember, plus or minus the square root of 1 over 64. And you can do that in the calculator. That would give you plus or minus 1 over 8. However, these are not the answers yet. So we don't have to do any more work. So this is the maximum number of answers. However, we did have problems before where we had to test out our answers. Remember with even root problems. If the problem started off with an even root, you have to check your answers. Logarithms, It's the same idea, unfortunately. You have to check your answers. The reason why, remember, logarithms, they don't like 0, and they do not like negative numbers. That pretty much implies tossing the negative here on the 1/8. So remember, this is referring to an x value, and that would ultimately end up being log of x. Log, the domain of log, prohibits 0 or negative numbers, so we're taking out a negative because of that. And thus we only have one answer. There's only one answer, and that's 1/8. So you need to get used to the idea of checking your answers with logarithms, and we'll see this theme pop up a few times throughout this homework set. Finally, we'll look at problem 4 here. And so, also, you might notice, I did not write a subscript, and you might see this theme a few times in the homework. When there is no subscript, it's understood to be a base of 10. And you can even write 10 if you want. So base of 10, base of 10. If they don't have one there, it's understood to be 10. And so you might notice, though, that this problem doesn't really fall into the format of the previous 3 problems. So we could try to make it match up in that way. So you can't really do the loop method, because that loop method that we did up here and down here, it requires 1 logarithm. Here we have 2 of them that are being added together. Well, hopefully you observe that if you have 2 logarithms that are being added together, then that means, and I wrote it up here, if you have 2 logarithms that can be added together, this is the product rule that we talked about in the previous section. This is the product rule, which tells us we can take this logarithm, combine those to give us 1 logarithm, provided we multiply. So notice there's the x, and here's the x minus 3, and the plus sign tells us to multiply. And the only reason we do that is so we can go from 2 logarithms to 1 logarithm, and now we can use this loop method over here. So let's go ahead and do that. And again, this tells us exactly how to format the exponential transition that we're going to use. It tells us that we would have 10 raised to the first power is equal to x times x minus 3. So that's the transition here. And from here, this is a lot more manageable to handle. So let's go ahead and clean this up a little bit, because here's a distribution, and we're ultimately going to have a quadratic. So when you simplify and reorganize everything, you will get exactly this. X times x is x squared, x times -3, -3x, and we're bringing the 10 over to become minus 10. And the only reason we did that is so we can factor. This seems to be x minus 5, and x plus 2, which will give us, well, go ahead and write them up here. This gives us 2 answers, as we've seen before. We get positive 5 from the first one and -2 from the second one. Now you might think, all right, we just did a sequence of steps, and now we're done. However, remember, we're still dealing with logarithms. And logarithms, you have to check your answers. Negative has to go. The -2 here has to go. 5 is okay. It satisfies the domain. So with that exception being thrown in, that would conclude these problems. So now we'll go ahead and move on to problems 5 and 6 from example 1. And so for problem 5, it doesn't necessarily fit any of the forms of the previous 4 problems. So Well, it has two logarithms, but they're not right next to each other, so we can't immediately go ahead and bring them together like we did in problem 4. So, and we also cannot use the loop method because that requires one logarithm. Of course, we have two. So the idea, or the motivation here rather, is let's go ahead and get these logarithms on the same exact side. So we'll go ahead and add log base 3 of x plus 1, that whole term, on both sides, so we can get the logarithms right next to each other. And so now the left-hand side, it's going to have both logs. So now it's going to be log base 3 of x minus 7 plus log base 3 of x plus 1. And now that's equal to just 2, because now we move the log base 3 of x plus 1 over to the left. And the only reason we did this is so we can utilize the product rule, which is a rule we can use when logarithms are being added together, like what we have here. So we can now modify this as a single log with the same base, and now we multiply. So all of this is still happening within the same log. In fact, you can put another set of parentheses containing everything if you'd like. So from here, now we have a single logarithm, and if you want to FOIL now, you can. I'm going to hold off a second, but now we have a single logarithm, and we can use that loop method. So remember, that method tells us you circle the 3 and you loop it around the 2 and have it point at what the logarithm is evaluating. So now we get 3 squared, so 3 to the second power is equal to x minus 7 times x plus 1. The next step, we can go ahead and simplify everything. So of course 3 squared is 9. And we can go ahead and FOIL this now if you haven't done so already. So the FOIL is of course x squared plus x minus 7x minus 7. And you might notice the x minus 7x, those are like terms. We can go ahead and combine those as negative 6x. So these two, we can go ahead and bring those together as negative 6x. We have a minus 7 here. This is a quadratic form, but we do need to set it equal to 0, so we have to bring the 9 over. So we're subtracting 9 on both sides. That gives us negative 16, which now we get x minus 8 and x plus 2. We can go ahead and put those answers here. So we factored it as such, and remember, each factor gives us a different solution. This one gives us positive 8, this one gives us negative 2. However, since the problem started off with a logarithm, we do have to check our answers. So notice there's a negative 2 here. And if we were to plug in that negative 2 into, say, the first parenthesis here, because it is an x, we plug negative 2 in for x, negative 2 minus 7 is negative 9, and log of negative 9 does not exist. We cannot take the logarithm of a negative number. So the negative 2 is outside the domain. 8 is okay though. 8 minus 7 is 1, and 1 can be evaluated by the logarithm. The 8 plus 1, that's positive 9, same idea. So we would only have one answer for this problem. A good rule of thumb, if you're given two solutions, generally the larger one ends up sticking around. So it's a good rule of thumb to keep in mind. Go ahead and move on to problem 6, and you may notice, yes, there is a fraction for a base, so that can happen. You can have a fraction as a base. And also, you might notice we have 2 logarithms. And kind of a theme throughout is if we cannot get logarithm equal to logarithm, then we want to condense this all down to a single logarithm. And so let's go ahead and use the latter option. We'll go ahead and take these two logarithms and break them or condense them down to a single logarithm. So this is subtraction. It's a difference of logarithms. And if we look at our available formulas here, we do have one that tells us what to do when there's a difference. It tells us use a quotient, i.e. use the quotient rule. So the quotient rule, that's what we're going to apply. So now we have a singular log with a base of 1 over 5. And the quotient rule tells us what goes in the numerator of the quotient and what goes in the denominator of the quotient. So all we did was combine these two logs as one log with the same base. So that is a base. And it tells us this goes in the numerator because it's on the positive side. This goes in the denominator. And now that we have a singular log, we can go ahead and rewrite it as an exponential. So using that same method as before. It tells us how to organize the exponential form. It tells us we have 1 over 5 to the negative second power is equal to x squared plus x divided by x squared minus x, just like that. And so we can go ahead and simplify this a little bit more. 1 over 5 to the negative second power, you can put that in your calculator, or you can think about it intuitively. A negative in the exponent means you flip the base, so that negative turns 1 over 5 into just 5, and 5 squared is 25. So if anything, this simplifies to 25. The fraction on the right can actually be simplified a little bit more, and it'll be helpful to do it now. And so kind of the motivation behind it, the numerator can be factored. The numerator, there's x's in both terms, so you can factor out an x. In the numerator, you can factor out an x from both terms, as I did here. So factored out an x plus 1. Denominator, same idea, it's just there's a minus. So that's what I went ahead and did here. And I noticed these x's cancel. And because they cancel, well, we get a much more simplistic fraction, and it'll help out, it'll make our computations a lot easier later on. So now what we have, I'll go ahead and write it up over here. So this is 25 is equal to x plus 1 divided by x minus 1. And we can go ahead and clear out the denominator, multiply it out. So multiply x minus 1 on both sides. That'll cancel it here. And we get 25 times x minus 1 is equal to x plus 1. And from here, it's a linear equation. You can go ahead and multiply everything out, combine like terms, and get a final answer. So ultimately, you will get 26 over 24, but my math lab wants a simplified fraction. That'll be 13 over 12. And technically, you would have to check your answer, but 13 over 12, it's positive. Everything up here seems to be mostly positive values, and for reasons I won't get into, it'll be positive here. So the way you can think about it is just positive is good. But other than that, that'll conclude these two. To conclude example 1, we'll go ahead and do problems 7 and 8. So problem 7 is probably the most exceptional problem in the first cluster of problems. And the reason why is problem 7, because we're squaring a log, so this isn't log base 2 of x squared, In other words, you cannot bring the 2 up to the very front. Instead, this is a logarithm squared, and kind of because of that idea, this resembles a quadratic form. We have to use U substitution here, ultimately. And so there's going to be a few more substitution-based problems in this section, and this problem kind of hints towards that theme. But the U substitution is going to be, it might or might not be visible what the quadratic form is. It's going to be U squared minus 3U is equal to 4, as we'll go ahead and write out in a bit. And so if this is U, then that reflects as U squared. So U squared minus 3, and now this is U, is equal to 4. And this is a quadratic, so we need to bump the 4 over, and it will be U squared minus 3U minus 4 is equal to 0. We can go ahead and factor. The factorization seems to be U minus 4, U plus 1 is equal to 0. And from here, we simply get that U is equal to positive 4 and negative 1 from both factors, each factor giving a different 0. But remember, when we did the U substitution-based problems, we don't accept the U values as our final answer. We have to convert them back to X values. And so that means, well, what I generally did was I would rewrite the rule, and with the rule comes, well, what happens to each U value that we found. So that gives us 2 situations. One of the U's we found was 4. So now we have 4 is equal to log base 2 of X. The other U is negative 1. So negative 1 is equal to log base 2 of X. And so we want to go ahead and solve both of these for X. Now it is a single log, which means we can use the loop method. There's no numbers in front of the logs. However, our visualization tends to help whenever the log is on the left-hand side of the equation, like what we had up here. That way when we loop around, we actually have something to refer to. So I'll go ahead and simply rewrite this. So all I did was switch sides. Because from here, now when we circle the base and loop around, we actually have something we can reference as an exponent. So this tells us that 2 raised to the 4 is equal to X. Or in other words, X is 16, because that's simply 2 to the 4th. Over here, the same idea. You will end up getting X is equal to 2 raised to the negative 1, which is 1/2. And so notice, both of these answers are positive. I did mention a rule of thumb that the larger answer generally works. We did get 2 positive answers, and just having log of X means that they both work. So both of these would be your answer for problem 7. We'll move on to problem 8, which really isn't that bad. It's just a lot of logarithms, but it really works out a lot more nicely than you think. Now, there are logarithms that are separated by a minus sign, and then these separated by a minus sign. Well, that immediately motivates, on both the left-hand side and the right-hand side, the quotient rule. So let's go ahead and do that. So the quotient rule, because of the minus, we can combine those, and this is log base A. We don't know what A is, but we don't need to know what A is, as we'll see in a bit. But the quotient rule tells us The x minus 3 goes on top, the x plus 10 goes on the bottom, and we'll follow with the equal sign and apply the same idea, because now we have another set of logarithms that are separated by a minus sign. So same idea. So x minus 4 is in the numerator, x plus 5 is in the denominator. And now, it turns out we have a log is equal to a log with no interference whatsoever. That means that the logarithm notation cancels out. We don't have this situation too often, but if we do it, it works out very nicely. And so now what we get is simply what the logarithms we're evaluating. Those are left over. So now it's a matter of, well, solving this type of problem. And so from here, we can cross multiply. So cross multiplication, or clearing out the denominators rather, yields exactly this. We will have to FOIL on both sides. And I will go ahead and combine the like terms. It'll be negative 3x plus 5x, which gives you 2x here. Now we get here. Let me make sure I did my math okay. Okay, cool. So now that we're here, we can go ahead and combine like terms. The x squareds are like terms, but they end up canceling each other out. So if you subtract x squared on both sides, they both cancel. Additionally, you can go ahead and subtract 2x on both sides and add 40 on both sides. So when you do all of that, so subtract 2x, add 40, so cancels here, cancels here. So what is that? It's 25 is equal to 4x. In other words, x is equal to 25 divided by 4. And it seems like that would be the answer for problem number 8. And conclude example 1. So now we move on to example 2. And what these collection of problems focus on is, well, going the opposite direction. We have exponential equations, and we want to convert these to logarithmic equations and see how that will help us find x. Normally these are exemplified by when the variable is stuck in the exponent, and these problems tend to be a bit intense with the algebra, so please try to stay along with everything. So as we've talked about these before, we've had problems like this in the past where if you have stuff like this, what we were doing in the section on exponential equations was trying to get 81 to have the same base, so that way we can cancel out the like bases. So for a problem like this, we would change 81 as 9 squared, and the only reason that we would make that modification is because the 9's would cancel out, and we would be left with the exponents. So just like that. But the question arises, well, what happens when you're in a situation where you cannot write a number as a base of the other number? And this is when we're going to generalize this idea, because this idea, it works in a very specific situation when we have two numbers that are related by powers. But over here, the generalization and the theme that we're going to be using throughout the remainder of these problems is, and this is a rule of thumb, whenever you have your variable stuck in the exponent, you can use a natural log to get it out. And how, when I say get it out of the exponent, I'm referring to utilizing the power rule here. So let's go ahead and demonstrate what I'm referring to. So here, there's a variable in the exponent. We definitely cannot write 3.8 with a base of 8. They're not compatible. So what we want to do, the first step of what I said was simply apply the natural log on both sides. So this first step, all I did was write ln. That's it. Nothing else so far. So I just wrote ln in front, ln in front. Now we're going to utilize the power rule down here, which tells us that we can take any exponent and bring it to the very front of the corresponding logarithm. Remember, ln is a special type of logarithm, so all the properties still apply. So we're bringing negative x to the very front. So if anything now, x is a product. The x is being multiplied by, well, a negative sign and by the natural log of 8. And if it helps you, this is exactly what's going on right now. It's just x times the negative natural log of 8. It's the same thing. These are the same exact thing. I'm just switching the terms. So if you identify that that is in fact a product, then all you have to do is divide and you're done. So upon division, that tells you that x is now equal to ln of 3.8 divided by, well, everything we are dividing. And you will notice with these problems, in fact, I wrote it down in my notes as well. So it says express irrational solutions in exact form and then as a decimal rounded to 3 decimal places. So this would actually be the exact form right here. And you can leave the parentheses in the denominator. I checked it and it accepted that. So this would be the exact form, but then it also turns around and says, go ahead and punch that in the calculator and round it to 3 decimal places. So as I mentioned, the ln button, it's the third button on the far left column. So I will type in ln of 3.8, close that first parenthesis. I'm putting in as many parentheses as I see up here. Divided by, the reason I recommend using parentheses for the denominator is so you will remember to put parentheses in your calculator. So I'm going to put parenthesis, negative ln, it opens a parenthesis for me, an 8, close parenthesis, and from there I get negative 0.642. I'm going to round up. I'm going to round up in this case because we're rounding to 3 decimal places, so this rounds to negative 0.642. And so this will be, as well as the remaining problems, it will want the exact form, so you would put this one in first, and then the decimal to 3 decimal places. So that will conclude the second problem. And we'll move on to this one here, which is fairly similar. However, we do not want to apply the natural log yet. We want to, as we did before, we didn't want to apply any rules until we got the logarithm by itself. So same idea here, we want to get the exponential by itself. Here's the exponential in parentheses. The 9 is not a part of that exponent. So we cannot bring the 9 as an exponent because there's no log. We have to divide it. We're going to divide both sides by 9, and when we do that, it does make the right-hand side a little messy, but at least the exponent is by itself. And now, well, 5 over 9 definitely cannot be written with a base of 6, so we have to apply that natural log rule again. So it's going to be the same type of problem as up here. So the rule starts off, simply just write the notation. And definitely remember, you have to do it on both sides. Whatever you do to one side, you have to do to the other. But that rule allows us to evoke the power rule, just like that. So now the 6, the base of 6 is by itself because the exponent came to the front. The ln of 5 over 9 stays. And now we can rewrite this the same way we did going from here to here. In fact, I'll visualize that right here. It is the same thing as x times 2 natural log of 6 is equal to the natural log of 5 over 9. So all I did between here and here, I just rearranged how the product looks. Instead of 2 times x times ln of 6, it's x times 2 times ln of 6. And I only do that so I can emphasize this product, and we know what to divide, as we did over here. So now, this is ln of 5 divided by 9 in this natural log, divided by parentheses 2 ln of 6. And I'm keeping the parentheses. So as I said, these problems, they get pretty intense. They get fairly intricate. So that's why I want to make sure you understand step by step what's going on here. And so this would actually be your exact answer right here. And we do have to figure out this answer approximated to 3 decimal places. So again, I recommend the parentheses because it reminds you to do it in your calculator. So ln, I'll put 5 divided by 9, I'll close that parenthesis, I'll divide, open up a parenthesis, and then a 2, ln, 6, close and close parenthesis. And it seems like I get negative 0.164 because 3 decimal places. So negative 0.164. Let me make sure that's right. Yes. So this would be your exact answer on the top, and then after that it will ask for the decimal approximation, and that would be that answer. We'll go ahead and look at problem 4 here as well, which they're trying to trick you by throwing in pi and e. Just there's some numbers, there's some placeholders, but it's still the same idea. Don't let the symbolism confuse you. If you see variables that are stuck in the exponent, you should think of this ln idea. So the ln idea, again, you apply the ln, something that you might have noticed, ln and e are right next to each other. So it just so happens in this problem, remember e and ln are inverses. We've talked about this in previous sections. So they cancel. ln and pi, they don't really have any relation. So over here, we're going to evoke that power rule idea. This is why we're using the ln, because the natural log helps us bring the power out of the exponent and makes it a factor, as it's called. Now the exponent is 1 minus x, so I'm going to keep that in parentheses, just like this. 1 minus x, natural log of, well, pi, because that's what's left over. over on the right-hand side, we don't even have to bring the exponent to the front. The 2x just drops down, just like that. And from here, so you might notice there's an x over here and there's an x over here. We need to get those x's together, which means we need to get this x out of the parentheses. We will have to distribute the natural log of pi. That is one number, that's one quantity. So we're multiplying this whole term, we're distributing it to the 1 and to this negative x here. 1 times natural log of pi is still natural log of pi. And then minus x, natural log of pi. So now that we got the x out of the parentheses, we can go ahead and get all the x terms on the same side of the equal sign. If you don't remember why we do this, you will see momentarily. So all we're doing is adding this term on both sides. We're bringing this term over because we want all the x terms on the same side. So just like this. And the reason why we do that, we've done this a few times before. The reason why is because now everything on the right, we forced it all to have an x in common. So ln of pi stays, and that's equal to, we can factor out the common x. And when we do that, we're left with 2 plus ln of pi. We're left with 2 plus ln of pi. And from here, as we did in this step here, and this step right here, we can now see what we have to divide by to finally get x by itself. So now x is ln of pi divided by, and I'll keep the parentheses, 2 plus ln of pi. And that's the exact answer. If you're wondering, can the ln of pi's cancel? The answer is no, they cannot cancel. That 2 is getting in the way. But now we have to figure out this answer as, well, we have to round it to 3 decimal places. And pi on the calculator is the 4th button on the first column. So I'm going to do ln, it opens up a parenthesis for me, pi, close parenthesis, divided by, open parenthesis, 2 plus ln of pi, close, close. I get 0.364. And that seems correct. So that would be the exact answer, and the decimal version rounded to 3 decimal places, and that would conclude the first 4 for this example. So we'll go ahead and look at problems 5 and 6, and you might notice they're not in the form of the previous 4, primarily because we do not have something along the lines of exponential is equal to number, or exponent is equal to exponent. In fact, there's 3 terms now, and really no way of combining all of these together. Now, one thing you might notice is that both of these forms they're actually quadratic in form. They have 3 terms equal to 0. That's normally a pretty strong indication of a quadratic form, which always has that insinuation of the u substitution. So these problems will evoke the u substitution, and in particular, you're probably thinking, well, what could the u substitution be? It's kind of hard to see in this problem, and even harder to see in this problem. Over here, it might be more clear to see that 2 raised to the 2x, this is equal to So this is using one of the exponential properties. This is 2 to the x quantity squared. Because remember, when you have an exponent raised to an exponent, you multiply the exponents together. And so by making that observation, you would see that the u here would be 2 raised to the x, because that's the repetition here. And then there's a square to give this the u squared term. So here, the u is going to be 2 raised to the x power. And so when we replace each one of these with u, so now it's u squared plus u minus 42 is equal to 0. Well, fortunately, we have a fairly tolerable quadratic we can go ahead and factor. Seems to be u plus 7, u minus 6 is equal to 0. And from here, we see that u would be negative 7 and positive 6 from each factor. But remember, anytime we use a u substitution, we have to convert back to x's. So let's remind ourselves of the rule. The rule is u is equal to 2 raised to the x, and we have 2 u values. So we do this for each u value. So now negative 7 is equal to 2 raised to the x, and 6 is equal to 2 raised to the x. Now, there is a problem over here. So this would go back to the problems we were looking at in the first 4. If you were to take the natural log of both sides, as we were doing for the previous ones, then you might notice that we're taking the natural log of a negative number, and you cannot take the natural log of a negative number. So actually we get a domain error, just like if you were taking the square root of a negative. It's the same idea. So with this one right here, you can just get rid of it. Another way you can think about it, an exponential function will never output a negative. And if you forget about that rule, just take it one step further, and you will, if you put this in your calculator, it will say domain error. So exponential cannot output a negative. But over here, this one's fine. And we can do the natural log process. So this would be natural log of 6 is equal to natural log of 2 raised to the x power. And from here, we can shift the x to the front as a factor. So that is ln of 6 is equal to x ln of 2. Finally, all we have to do is divide by the natural log of 2 to get x by itself, because that's a product. And that would be our only exact answer. But of course, it will want the decimal approximation as well. So we have to go ahead and throw that in the calculator real quick. Natural log of 6 divided by natural log of 2. I seem to get 2.585. And this would represent the 2 answers that problem number 5 is looking for. We'll go ahead and move on to example 6 here. So this one's a little bit more elaborate, as I mentioned before. It's elaborate because, well, it's not clear what this common base is. Over here, at least we saw that 2 was this recurring theme. Over here, well, it so happens 49 and 7 are fairly closely related. In fact, 49 is simply 7 squared. Also, something else, this exponent has x plus 1. So we're going to go ahead and break up that exponent using another rule of ours. that is the same thing as 7 to the x power times 7 to the first power. This is an exponential rule that we've utilized before. And we utilize it here so we can start to get a middle term that we can designate as our u for the u substitution. So we see a 7 raised to the x here, and over here, this is the same thing as 7 to the 2 times x. We'll go ahead and rearrange the terms here. Now we get here, and notice this first term is just like the 2 raised to the 2x we had before. So we could apply the same logic, but ultimately we see that the recurring theme here, similar to the last problem, is that u is going to equal 7 raised to the x. And from here, the 7 to the 2x breaks apart the same way that this one broke apart right here. So this would be u squared plus 7 times u, so 7 times u minus 78 is equal to 0. That's what it looks like as a corresponding u substitution. So these problems, they're definitely a bit intricate, and that's why I'm trying to explain it very slowly. We can go ahead and factor this though. I think it was 6 and 13 for problem 6, yes. So this was u plus 13 and u minus 6 for the factorization, which gives us u is equal to negative 13 and positive 6. But remember, u's are not good enough. We have to convert back to x's. So let's remind ourselves of the rule. And we'll go ahead and see how both of these numbers fare. So one of the u's is negative 13. The other u is positive 6. You might have noticed already, an exponential cannot output a negative. If you don't see that immediately when you apply the natural log, you will notice the natural log of a negative cannot happen. So we can toss that answer. So we'll go ahead and just focus on the 6 is equal to 7x portion. And from here we can apply the natural log of both sides. Let's see, I might be running out of room here. So we'll go ahead and bring this down here. And this allows us to bring the exponent to the front. Just like this. And finally, we can divide both sides by natural log of 7 to get x by itself. This gives us our exact answer, and again, we need to round this to 3 decimal places. And I get 0.921 from rounding to 3 decimal places. And that would conclude problem 6. To conclude example 2, we'll go ahead and do problems 7 and 8. So for problem 7, what makes this one different is the negative exponent, which means that we can't use u substitution yet. We do have to be reminded of what the negative exponent means. So what it refers to is taking whatever the base is and putting it in the denominator. So now what we're going to have is 5 to the positive x. It's the negative part of the exponent that sends the 5x to the denominator. And it's right next to the 48 by multiplication. But by the mere fact that there is a denominator term, that does motivate clearing the denominator. So we multiply everything by 5 raised to the x. So 5 raised to the x, so we're multiplying by the least common denominator. And over here in the middle, these two cancel. And what we have now is 5 raised to the x times 5 raised to the x. That's going to be 5 raised to the x squared minus 48, since the 5x cancel, it's just 48, is equal to 2 times 5 raised to the x. And now it might be a little bit more evident with the 5x's here that our u substitution, well, now we can apply it the same way we did in the previous problems. The u substitution here is 5 raised to the x. And so the way that is shown here, we now have u squared, because u is 5 raised to the x. So that is u squared minus 48 is equal to 2 times u, or just 2u. This is a quadratic, so we need to bring the 2u over via subtraction. So that is u squared minus 2u minus 48 is equal to 0. And let's go ahead and factor. So this should be u minus 8 and u plus 6, which gives us 8 and negative 6 as our u's. But just like the previous two problems, this isn't good enough. We need to solve for x's. So if we remind ourselves of the rule being u is equal to 5 raised to the x, then we have two different situations. And these regard to each u value that we found. So u is 8 in one situation, and u is negative 6 in another. But hopefully you can see that the negative 6, we can toss that solution because exponents cannot output a negative, or if you apply the natural log, you would derive that. I won't do it here, but we can toss that solution. So we'll focus on primarily this one, which means just like the previous ones, we apply the natural log. It allows us to bring the exponent to the front. Finally, we just simply divide by natural log of 5 to get x by itself. So here's the exact answer, and the decimal approximation. We'll end up getting natural log of 8 divided by natural log of 5, 1.292. Yes, so 1.292. So that would be the answer for number 7 here. And number 8, so it's kind of strange because number 8 technically doesn't fall under the same category as the rest of them. It honestly falls under the same category as the beginning set of problems, maybe a problem 1, really. So I wanted to show you all this because it looks very messy. So there is kind of this idea of a common base going on, but there's this fourth root in the way. Do you remember, or hopefully you remember, what a fourth root represents? A fourth root is the same thing as a 1/4 power. And the reason why I'm mentioning that is because when you have an exponent, or an exponential raised to an exponent, you can multiply the exponents together. Just like that. And once you have this, then you can cancel out the common bases like we did in that first problem of example 2. So the 2's cancel, everything else drops down. So that would be 1 over 4 times 3 minus x is equal to x squared. And it is a quadratic. So here we can multiply both sides by 4. I do see a least common denominator, so that motivates multiplying as such. So multiplying both sides by 4 would yield 3 minus x, because the 4's would cancel, and then 4 would not cancel over here. So this would be 0 is equal to 4x squared plus x minus 3. And by, I guess, limitation of space, I'm just going to go ahead and put up the factorization. Pretty sure it is this. Oh, no, I'm wrong. Try that again. Minus 3 here, plus 1 here. Okay, that should be better. Let me make sure. Okay, 4x. Okay. So this would be the correct factorization. From here, we get, or you can use a slide and divide or whatever method you're comfortable with. You get 2 answers from this. Whenever the first term is equal to 0, and whenever the second factor is equal to 0. And from this one, you get 3 over 4. And you might think, all right, so we get -1, we toss that answer, right? We do not have to toss the answer, because we never had any logarithms. We only had to do that when we had logarithms. So here, both of these answers would actually be part of your solution set. And that would conclude, actually, example 2. So you conclude this section, we're going to go ahead and finish up example 3. And so example 3 is the application-based problem at the end of your homework set. So it throws a bunch of words your way, and it does mention a function. So I went ahead and wrote down the function. And it also, so the last sentence, it says, when will the population reach 396 million people? So when you look up at the equation here, you see P for, well, population, and T is for time. So when it gives 396 million people, it's giving you a p-value. So 396, this is in millions, so I can leave that. And it wants to know how much time will that take. And this problem is a bit of a precursor towards the type of problems you will see in the next section, which are, it's less problems, but they're all applications. And so we'll be applying this process as such. So we're trying to get t by itself. So the variable is in the exponent, which normally motivates using the natural log, as we did in the previous few problems. However, the exponent is not yet, the exponential function is not yet isolated. This would be the exponential, and this part, we need to move it to the other side. In fact, this problem resembles problem 3. We have to divide 281 on both sides to get the exponential function by itself. And so over here, the 281s cancel. And now we have 396 divided by 281 is equal to 1.010, all of that raised to the t minus 1997. And now that we have the exponential part isolated, we can apply the natural log to both sides, as we did before. So Instead of rewriting it, I'm just going to write the ln notation in front, just like that. And from here, we can go ahead and bring the exponent to the very front of the corresponding natural log. So just like that. And the way this will look now, so the left-hand side will stay the same. Natural log of 396 divided by 281 is equal to t minus 1997. And we will keep that exponent in parentheses because it is a singular exponent. The natural log of 1.010. And now what we can go ahead and do is divide both sides by the natural log of 1.010. That would get the t minus 1997 by itself. So let's go ahead and do that. Divide both sides by natural log of 1.010. And so over here, these cancel. And what we have follows straight from right here. So finally, all we have to do is add both sides by 1997, and this will get t by itself. And you will have to put this in your calculator because the problem wants you to find a decimal and round it to the nearest whole number. So if you follow all the parentheses accurately, then the right answer will come out very nicely. So natural log of, and it opens a parenthesis for you, 396 divided by 281, close parentheses, divided by ln of 1.010, close parentheses, plus 1997. And you should get 2031, which translates to the population will reach 396 million people by the year 2031. And that would conclude this section.